So welcome to the Picture Language Seminar. This is our first seminar this fall, and we're looking forward to having other ones. And today it's really a great pleasure to have Yasuyuki Kawahigashi. He's visiting from the University of Tokyo. He'll be here for the rest of the week, and we're looking forward to having your talk. It's going to be about fusion categories, tensor networks, and operator algebras.
Okay. So, thank you very much. I'm very glad to be at Harvard again. I think this is my sixth visit to Harvard University. Yeah, this is a very nice place. So today I'd like to talk about unitary fusion categories, actually realization of unitary fusion categories based on operator algebras and using tensor networks. This is basically a topic of my talk, and also this is what the title says. So, is okay. So I assume that you are familiar with this notion. I often draw projective, but I always talk about the unitary structure. And there are lots of different realization of such a category. Sometimes with operator algebras, sometimes without operator algebras, like for example, quantum groups or vertex operator algebras or whatever. But yeah, I'm an operator algebraist, so I would like to understand structures of unitary fusion categories using operator algebra. Then the main theory to deal with this kind of topic is Jones' theory of subfactors. So this is some nice inclusion of operator algebra, von Neumann algebra. So nice von Neumann algebra is called a factor. So this is an inclusion of one factor into another factor. So this is called a subfactor. Then the larger algebra is regarded as an n dimension. So we just restrict the action of m to subalgebra. Then this is trivially n dimension. Then in a typical situation, this has some kind of reducibility. But then we can make a relative tensor product over n over an algebra. So this is something like a tensor product of modules, bimodules over a ring in algebraic setting. So this is some functional analytic version. So this is a tensor product over an algebra that can be defined in some nice way. Then typically this is not irreducible anymore. So we make an irreducible decomposition. And we repeat this procedure reducible decomposition. Then, so we get more and more pieces of irreducible bimodules. So typically, this procedure does not terminate. So we get countably many mutually non-isomorphic bimodules, irreducible bimodules this way. But in some very nice situation, we get only finitely many irreducible bimodules up to natural isomorphism. Is it visible?
It's good.
This kind of finiteness is important in many different fields of mathematics and also physics. For example, this kind of finiteness is often called rationality. In a conformal uniform or in the setting of quantum groups. This name comes from the fact that if we have this kind of finiteness, some parameter takes rational values. So in this setting, we have finitely many irreducible bi-modules. So they are irreducible bi-modules. Then actually, this setting, it turns out that they are closed under relative tensor form. X, I, tensor, J. Okay, I drop N. So this is a fusion. And also we have a dual bi-module. So this is a rigid tensor category with finitely many irreducible objects, so we get a fusion category. Okay, as a trivial object. This is part of that one. So this is a trivial. So we get a fusion module. Then, so this part is also visible. Yeah. Actually, it turned out that all unitary fusion categories are realized in this way. This is quite non-trivial, but if you know for many years, operator algebra. So I draw some diagram. So the object in the bi-module and the morphism of the like and n. So morphism is bi-module homomorphism, which means that we have a Barge linear map from this Hilbert space to another Hilbert space, and this has to commute with the left action and the right action. And also the tensor product. But now, so this is well known for many years, more than 30 years in operator algebra theory. But today I'd like to talk about something different. So this is tensor. So this kind of thing is well known in operator algebra theory, and actually many people worked on this kind of thing in the 90s, but for last say 30 years, for the combinatorial aspects, we don't have much progress. This was a kind of old topic. But recently, physics people in two-dimensional topological order, they kind of rediscovered a very similar, essentially the same structure. So we have a renewed interest of this kind of old topic, subfactors. And then it turns out that from their viewpoint, we can find some new problems in mathematical aspects of operator algebras, and also we can produce some new solution to their problems from operator algebraic viewpoint. So through this kind of interaction between operator algebras and their physics approach, we have some new results, new problems, and new interests.
It's over there.
So I'd like to explain this one. Well, first, I just show the answers to these entries without really explaining details. So actually, the answer is 4 tensor. It's this. And here we have some labels. So, I guess you are familiar with some tensor transformation. Like 1 tensor is a vector, 2 tensor is a matrix, and so on. So 4 tensor is just a finite family of complex numbers indexed by 4 labels. Then, so here, but then, so this is an object. So here we have a tensor product. The tensor product is, and also here in this setting, I assume that all indices can be in a different sets. So all the 4 index sets can be different. And then we have a tensor product. Yeah. So this is a vertical concatenation. So here, this index set and this index set have to be the same to make this concatenation. But under that assumption, we can take just a vertical concatenation. And so in this setting, vertical direction and horizontal direction are symmetric. So we have to fix some convention to distinguish these two. And just this is a standard convention in the physics paper. And then this is vertical concatenation. And then, so this is the convention. And also, we need some notion of irreducibility, but for that, we need a direct. Or in the case of bimodule, a direct sum is quite easy, just a direct sum of Hilbert spaces. But here, direct sum is like this one. But then for this, so we have 2 tensors. And then for making this direct sum, this must be these 2 index sets should be the same. And also these 2 must be the same. Otherwise, we cannot make the direct sum. So these 2 are the same, these 2 are the same. Then these 2 can be different, and these 2 can be different. But so this index set is 1, this is 2, 3, 4. Then this part is the union of 1 plus 3. It's the union of 2, 4. Okay, so here we have 2 index sets, and we make a disjoint union of these 2, and we make a disjoint of union of these 2. Then this is just 3 bases. So if we use 1 and 2, just use the original value. And if we use 3 and 4, we use the original value of y. And otherwise, if, for example, if we use 1, here 1 from the set 1, here we use something from set 4, we get 0. So this is just a direct sum of a matrix. So we have diagonal sum of 2 matrices and off diagonal paths are 0. So, then another thing is a unitary equivalence. So we have X. Then here we have some unitary matrix like this. And this is the unitary equivalent. So this is basically a definition of a unitary equivalent. Then, so irreducibility, I mean that a tensor, a four tensor, no,
To zoom out.
decompose into a direction after any unitary equivalent. So whatever unitary you and D we choose, after applying these two unitary matrices, we still do not have a direct sum decomposition. That's the definition of reducibility. Then, also the morphism is basically this kind of thing. So we use the same one. Yeah, okay. A bit complicated. Yeah, yes. This is all basically intertwined with this one, but here it can be different. And so this is an intertwined. And F prime are somehow related to the pair. So if F goes over X, it becomes Y and it changes to F prime. This kind of pair with a motion of intertwined. So this kind of thing has been studied by physics. So the paper I mainly sorry. This is the source of this kind of thing, and many people follow this paper. Then, so this is an So at least on the formal level, everything looks fine. But actually, this paper, so this is really a physical paper, so they have no definition, no theorem, no proof. And it's hard for mathematicians, it's difficult to understand what kind of assumptions are really made and what kind of arguments are really necessary to get desired conclusions. Then using operator algebra, we can really understand if they are exactly the same thing. So this is what I learned today. Then, so then I have to explain how four tensor arises in operator algebra setting. And natural, yeah. And this is operator algebra. So in operator algebra, a subfactor is an inclusion of infinite dimensional algebras. So they are definitely infinite dimensional structure, but in a very nice typical situations, all the important information is encoded in finite dimensional structure. That's an important understanding of the nature. Then important notion is for the commuting is clear. So this was first introduced by Popper many years ago in a different context and studied extensively by John Soknian and others. So this is a typical situation. We have finite dimension. This. So now instead of two algebras, we have four algebras, but all are finite dimension fixed algebra. And the finite dimensional fixed algebra is just a direct sum, finite direct sum of matrix algebra. So for example, A is like something like 2 by 2 plus 3 by 3 plus say 5 by 5, for example. This thing. And also say B is yeah, for example, this kind of thing. Then actually, so if we have the inclusion of this kind of finite dimensional fixed algebras, so here this 5 in this particular example, for example, this 5 is 2 plus 3. So it means that this is an embedding. So it means that this 2 by 2 matrix and this 3 by 3 matrix, they just have a direct sum and off diagonal path are 0. This is an embedding of this one into this. And so here we have 11, and 11 is 3 plus 3 plus 5. So here we have multiplicity 2, like this. So this 3 by 3 matrix is embedded into this 11 by 11 matrix with multiplicity 2. And this one is embedded with multiplicity 1. So twice 3 plus 5 is 11. Okay, so this is a typical situation, and actually always embedded with this way. So from this kind of embedding, we do have this kind of graph. And this graph is called a graph. Then here we have 4 inclusions, so we get 4 bracket diagrams. So we have A, B, C, D, and some graphs like this one, like this. Then here we fix one direct sum A and choose one edge here. That gives an embedding of this one here. And choose another edge here. That gives an embedding of this direct sum into D. And also here we have another edge, Then it gives another embedding of this direct sum into D. So if we have two edges here, they give 2 ways of embedding of this one direct sum into another direct sum here. Then by comparing these 2 embeddings, we get a number. Complex number. So in this way, from each, so this is a square, so we choose 4 edges and also these vertices must be the same. These should be the same. So we get a closed square. So each closed square gives a number. Then to this point, everything is totally elementary. But now the non-trivial point comes next. So here, I didn't assume anything about this inclusion, but the nice thing is this commuting square, which I did not explain yet. So the commuting square means this situation. So A here, B, C, D. Here we are using original inclusion, but here we use a different. So from A to B, we have an inclusion, but we also have the opposite direction. Actually, for factor here we need a trace. So it's basically a linear algebra trace, but here we have multiple direct command, so we have some weight for each direct command. So just a weighted sum of ordinary linear algebra trace. Then the trace gives an L2 norm, like these are like this. So this gives an inner product. So each is a finite dimension. So each becomes a Hilbert space with this inner product. Okay, everything is finite dimensional, so we don't have to make a completion. So each A, B, C, D is now Hilbert space by this inner product. Then we have this is the Hilbert subspace of P. So we have a Hilbert projection, orthogonal projection. So this is the projection. And also this is the projection. Then we use two projections horizontally and two embedding vertically. And if this commutes, we say this is a commuting. And this is a very important and natural condition. Yeah.
How do you choose which C star algebras you're working with? And are you choosing like D and then looking at what multiplicities might be allowed in A? Or
Yeah, so
like,
in this setting, I assume that something this is given with this trace, with this property. That's the initial data.
that's the initial.
Yeah.
Okay.
Then suppose this is given. Commuting square. Then we have a construction for the joint basic construction. So we can basically reflect this one. E1, E2, and so on. We can repeat. So this is a one step. So this is the original setting. This is the one step basic construction, which again gives a commuting square. So this is the second basic construction, and so on. Then in this way, we get increasing, so each is finite dimension. We get an increasing sequence of finite C star, finite dimensional C star. Then the third limit, we get an infinite dimensional operator. And that gives us some. This is a very important construction. And another thing is that so here we have a commuting square. Then this commuting square condition with a very severe constraint. On these four tensors. For these numbers. Actually, so I got the characterization of these four tensors in terms of the setting of this commuting square known or based by Hager, Skoll, and O'Neill. any other. So this is in today's understanding based on four tensors. So this is called bi-unitary. So this is graphically like this. So here we have some x. Then we have something like basically x bar. This is a horizontal reflection. So originally, this index set and this index set can be totally different. So we cannot compose them. But we have horizontal reflection. So now these two are the same, these two are the same, these two are the same. Okay, and also these two are the same, so we can concatenate. Then so we close this, and also we close this one. Okay. Then we have two more edges, two more edges. This is basically a connected mode. 1, 2, 3, 4, 2, 3, and 1. So this is like the kind of star. So this is a multiplication of x and x term, and we get the correct delta. So unitary, sorry, identity metric. So this is the kind of unitarity. And we have another unitarity. So we now close this one. And again, we get correct. So these two are the bi-unitarity. And actually, we have some correction. Arriving from some parent from this. And actually, these questions are important for actual computation, but conceptual this. So, this way these are real different. And yeah. Then, so this is a natural condition to consider from operator algebraic viewpoint. And it turns out that these are exactly the condition we need in the setting of tensor network in the physics. Actually, they never write down. Yeah, but and then I come back. So this is a construction from this is the initial. So from this finite dimensional data, we get infinite dimensional inclusion, but also we can come back a compact. So we start with a compact dimension. But with infinite dimensional. Then again, we have joint basic construction for this setting. So from the initial inclusion, we get a larger algebra. And so again, we can apply the same thing. So we get a larger and larger algebra. Everything is now infinite dimensional. But then we look at this kind. So this is a relative constant. So this is a set of all the operators in MK, which commute with everything in the small algebra. Then, so this is a large algebra, so the relative competence is larger. And then, so these are inclusion of four algebras. Then actually we need some finiteness assumption. Finite. This is a standard assumption. Then if we have some finiteness initially, then here, this is a commuting. So in this way, we can go back and forth. Finite dimensional commuting square and the subfactor. But this correspondence is not one-to-one. So we have commuting square and subfactor. But okay, I should. So we start with, okay, this way. So we start with this one, nice subfactor, and go to the left-hand side, commuting square, and apply this construction. Then, under some very nice condition, we get back this one. So in that sense, they really correspond to each other. But the converse is not true. So we start with the commuting square, and we go to the subfactor and come back. And then this is not, typically this is not the original.
Where does the bi-unitary condition come from?
Yeah, so here, this is, not bi-unitary, this is, this is the characterization of commuting square. So commuting square and bi-unitary connection are the same thing. So I said, if we this way, then that's this is original book. But the other way, not. And then we get the original one on these. The condition. Oh, fun. So this name, flat connection, comes from an analogy to differential geometry. So in differential geometry, we have a concept of flat connection. And this is somehow kind of discrete version of a flat connection. So this is why we use this name. And then, so the most recent results of mine for the relation between the two is an understanding of the intertwinements. So for understanding the intertwinement, we have three ways. So the first one is biology from this is standard. Yeah, biology. And the next one is bi-relative, okay, relative constant. Subfactor. Okay, maybe I should always. And three is flat sheet. For combining the connection. Then the fourth is tensor, two tensor. So they have a notion called Dipper condition, like this. So they are interested in the setting of intertwined design. When they use so now this is F is a three tensor between x tensor y and b. So this is a vertical concatenation. So this is an intertwiner two. So this is called the Dipper condition. Then in the setting, they use this property to represent the intertwiner. And from their setting, this is a natural function, natural condition for the intertwiner between four tensors. And here, so this is the most natural understanding for intertwiner in bi-unitary setting. And two is just a kind of translation into subfactor. Okay, so these are the ideas. And then, based on bi-unitary connection, we have some nice description of this kind of thing. This is an old thing known by many years ago. Then we can relate this to number 4. So that's a new thing. So flux field is the notion Newtonian many years ago. This is written in this way, x bar, and then this, C values. This is here you have say age. Yeah. Omega delta. So now you have a notion of the flux field. Then if we just translate this language into a tensor network picture, so this is concept. Then this kind of invariance. Here we use x bar. Here for these two are the same. And here we have project delta of this y. And then so this is a kind of invariance. So for these two tensors, we apply this kind of operator for the left, make the same thing on that. So it's basically an invariance of the sum projection. So it means that this F is in the range of some projection. And so this is the commutativity, basically, if we identify this one. So it's a kind of commutativity or intertwine. But then these two are the this can be proved in operator algebraic technique. That's my most recent result of this. On this way, we can really translate all the result and all the notions from one to the other, also vice versa. So the advantage of this kind of thing is so everything is finite. So the method based on operator algebra, like subfactors, there we have to use infinite dimensional operator algebra. there is another approach based on supersection vectors, but also they need infinite dimensional operator algebra. But here, in this approach based on 4 tensors, everything is finite dimensional, and in principle, they can be computed on ordinary computers today. So this is why physics people are interested in this, and so in my approach, we clarify all that assumption, normalization coefficient, and also all the assumptions. Then we can work out in concrete examples numerically based on different things. Actually, in their paper, they use only finite group examples, and beyond that, they cannot make computations because they don't know exact assumptions. But now everything. Yeah. Okay, so I stop here. Thank you very much.
Thank you very much for a beautiful talk, and I wonder if there's some questions.
I think recently there are many papers working on like those graphical representation of non-evaluable symmetry. And some people actually is here. I discussed with them. Do you think that this have some relation?
Yeah. Basically the same thing from different perspectives.
So what if you have a 5 tensor or
We use sometimes 5 things in a sense. Here we have 4H, but we have another one, labeled this. So in that sense, this is a 5 tensor, but thinking this way doesn't really give much advantage, so I don't know. Yeah, actually, in some world of tensor networks, they do use 5 tensors. But I don't know about 6 tensors.
And then a follow-up question is that because people already care about which type of topological code is universal. And then we only know maybe S3 is and Fibonacci code is. But can we directly see from this representation that okay, some of them can be written in a very efficient way, so it is not universal. Otherwise, it is universal.
All right, it's not clear.
Okay.
And also today I ignored the issue of braiding entirely. But yeah, braiding also can be understood differently.
So if we can construct a full set of like operation in of braiding and fusion in a way, and then it might not be
right. And also, in order to realize non-invertible symmetry, we really have to use this kind of thing, this correct coefficients. So all examples arising from group cycles, they are really inverted.
So this bi-unitary condition is very much like reflection positivity. If you replace the delta, you replace delta by something positive.
Right. Yeah, we have to get positive. Yes. Yeah, just one is observation or literally positivity. Yeah.
So if you do that, does it relate to something else other than this separate condition?
Yeah, that's an interesting thing to consider, but I just don't know.
Well, if there are no other questions, I'd like to thank Yasu again, and we really look forward to the rest of your visit here. Thank you.
Thank you.